Okay, let's look at this question from Summer 23, paper 4, variant 1, question 2C. All right. The complex tris-ethylene diamine chromium 2 plus ions exist as two stereoisomers, whereas the complex, this one here given, exists as 4 stereoisomers. Complete the three-dimensional diagram in figure 2.1 to show the 4 stereoisomers of the complex. Now, first, let's do a quick recap. The tris-ethylene diamine version, which is this one. Okay, now ethylene diamine is neutral, and ethylene diamine, they have a structure that looks something like this. Okay, so you have like a trapezium shape here. You clamp it in two corners of the octahedral. Okay, so this is your ethylene diamine or 1,2-diaminoethane. Short form is EN. Okay, and they are considered as a bidentate. So they give something that you're very familiar, which is the 3-ethylene diamine. We call tris-ethylene diamine version. Okay, and they exist as 2 stereoisomers. Now, the 2 stereoisomers over here will be the optical isomers. Okay, the left and the right hand mirror images of each other and are non-superimposable. And now the question gave us something new, which is a complex or a ligand that looks something like this. Okay, so if I were to open up the structure, okay, you realize it's like this. And it's also a bidentate, where one end uses an oxygen lone pair and the other end uses a nitrogen lone pair. Okay, still considered bidentate, something new, something you're not familiar, you have not seen it before, but it's fine. Okay, now, but the problem now is you want to draw 4 stereoisomers. Now, according to my previous video, I did brief you on the formula. All right, more or less like you see that this is a for the question now, original question, you get that this is a metal, capital N, with a bidentate AA3. So this one, immediately, it will show a optical isomerism, okay, which is what the question already stated. But the problem now is you have also something similar in the red color pen. You have a chromium metal, and then you also have a bidentate here, which is capital AA, and you have 3 of them. Okay, 3 of them. Now, what is the difference between the blue pen and the red pen? The blue pen uses nitrogen on both sides, the lone pair on nitrogen, and the red pen actually spices up the game a little bit. One end is oxygen and one end is nitrogen. Okay, so if you were to play like how the syllabus normally asks, the student will draw actually an optical isomers for the first 2. Maybe we shall start with that 2 first. Okay, so I will just randomly put the so-called ON bidentate, okay, on one of my diagram first. Okay, so you just randomly clamp in no particular order. Okay, so let me just clamp it. I just randomly do it something like this. Okay, now knowing that you have mirror images of each other, so what you want to do is you want to reflect mirror image, the near and the near. Okay, the far and the far one. Like this. So we have already 2. And this is according to how you normally solve capital M, capital AA, 3 of them. All right. So this is the first pair, so-called the 2 out of 4. Now they want you to use your creativity to come out the 3rd and the 4th isomer. Okay. So normally when you want to create isomers, right, which is something new, what you can do is you normally change one thing, and the rest is constant. It's like any science experiment. You only change one thing. You only have one independent variable. The rest must stay constant. Okay. So this time, okay, if you want to play by luck, all right, so you just randomly change one leg. So for example, okay, you want to change this particular leg. So let me just put in green color pen. I would like to just swap these 2. I'll just put it in green. And the rest, I just remain status quo. Okay, like this. And I reflect it. So we can see that this is also a mirror effect of my third and fourth drawing. Okay, so what actually I did was, normally when you want to create another isomer, we try to only swap one ligand, okay? As in only one thing that can be changed. So I only change it like this, from like this combination, I just change, the rest must stay constant, okay? Now, if you have the time in exam, you may want to rotate your structure. So let's give it number. So for easy referencing, structure 1, structure 2, structure 3, and structure 4. So 1 and 2 is already a confirmed answer. Now, what we need to do is, we need to check whether 3 is the same as 1. Okay, or is it the same as 2? Because if you can rotate the octahedral where your isomer 3 happens to be number 2 or number 1, that means your 3 is not a new isomer, rather it's a rotated form of 1 or rotated form of 2 in space. Okay, yeah, that is if you have time. But normally in paper 4, if you do not have enough time, right, you just try your luck. Okay, so now I'm just going to show you what I did was I only changed one leg. Okay, and the correct answer is actually on my drawing. What actually we did here behind the scene is, you want to check on 3-3 combination, which is where I'm going to highlight. You want to focus on the oxygen, the 3O. I just want you to put your attention on the 3O that I'm highlighting now. Okay, so you may want to look at structure number 1 first. Structure number 1, if you look at the 3 oxygen here, they are actually 90 degrees related to each other. Okay, this is 90. Okay, and this is 90. Correct? 90, 90. And we actually found a 180 here version. Okay, so you pick any 2 oxygen and you ask, what is the angle between the 2 oxygens? So we have a 90 version, a 90 version, and a 180 version. Okay, now, of course, isomer 2 will also have the same answer, like 90, 90, and 180. But if you look at isomer 3, right? These 2 oxygen, which let me highlight first, oxygen, oxygen, and oxygen. The 2 oxygen is 90. What about these 2 oxygen here? These 2 oxygen is 90, correct? Now, what about these 2 oxygen here? These 2 oxygen is also 90. So we can see here, the 3 oxygen in the 3 bidentate, right? They're aligned 90 degrees among each other. And of course, isomer 4 will follow all the 390 degrees. Okay, so we can see a distinctive difference between the first set, which is 1, 2, and the second set, 3, 4, where the 3 oxygens are either mutually cis. This is called mutually cis down here. Mutually cis. Cis means 90 degrees angle. Okay, so for isomer 3 and 4, right, they are mutually cis and they're just mirror effect of each other, because you need a minimum 2 bidentate. You can show optical isomerism, remember? Okay, so 3, 4 is a mutually cis connection, all right? And for your isomer 1 and 2, right, you have at least one relationship, which is 180, all right? That one is under trans. You have cis, and you have one trans, which is 180 in the first isomer and the second isomer, all right? So that is actually how we are able to create another pair of optical isomer. Now, what I did was basically I changed one ligand position. You cannot be changing 2, you only change 1. Normally, just work one thing at one time, okay? And you have the time. If you have the time, you can try this to rotate my isomer 3 and see whether does it coincide. So-called, would you be able to rotate isomer 3 to look something like isomer 2 and isomer 1? The answer is you won't be able to rotate it back to look like isomer 2 or isomer 1 in 3D space. All right, so that is how I come up with the third isomer, and I mirror effect it to the fourth isomer. So this is a very, very new type of question. All right, so you want, you can try. Okay.